morning. We welcome you, Chuan Li from Twente University, who will talk about bismuth selenide nanoplates.
Yeah, of course, I really like to thank the organizers and for inviting me on the event. And it's really my pleasure to come back, and it feels really good to come here and time to time and to discuss nice physics. So today I'm gonna talk about our pretty recent work on this bismuth selenide nanoplates. I think in the morning we had very nice introduction from Professor Oleg Vanov about this runner-related physics, and I think from this at least yes, much longer now. The initial and a lot of work has been put in to this direction is in combination of the topological states and the conventional superconductors. So that's many cases Josephson junction type devices. So in our case, we are also gonna taking this topological material approach and to see whether we have some possibility to probe this relevant physics and to be a little bit more precisely. For example, this is really involves some edge states in combination with the superconductor and induce superconductivity and the Josephson effect in such kind of topological edge state. And here, and I think I don't need that much introduction about the topological material. It's simply I want to convey a little bit the idea about having different dimensions for these topological states. For starters, I think here, if you have a 3D material, of course, you can, if you're in a topological regime, you will have the 2D surface states around the material, and these surface states are usually with this direct Hamiltonian, direct phone shape, and one of the most important property we always employ here is the spin momentum locking. So of the opposite momentum, you have opposite spins. Okay, and this naturally protects this from the backscattering. However, the tricky thing here, if you have a 2D material, 2D surfaces, first, your backscatter is kind of fully forbidden from this direct scattering. However, the processes are allowed to have an intermediate steps. So if you have such kind of intermediate states, the total backscattering rate will not be zero. It's finite. Okay, and then here comes to this another aspect. Like you can also lower the dimension of the material. Okay, so the similar phase transition and just in a little bit lower, not one lower dimension, you could now have a 2D bulk states with 1D edge channels. In this case, it's also called quantum spin-off effects. And in this case, your code given by a 2D, of course, 2D states, and in this case, there are no other choices. They have to be, backscatter into each other. That is much stronger suppressed process. So that's why I think in some aspects, these lower dimensions give you stronger protections in your topological states. Okay, as we talk about the topological insulator, there are also many other different types of topological material exist in the world. One of these very interesting and beautiful system is this called wild semi-metal systems, and they break the symmetry, like Tamerson symmetry or inverted symmetries, and this naturally forms this so-called Fermi arcs when you projected two wild cones to the surfaces, and by giving such kind of cuts in between the two separated wild cones, you can get very similar topological state at the surface. Of course, you can see the difference is, well, they have to go from one surfaces and to another surface will be completely purple. And beyond this, I think very recently many work has been done on this higher order topological state. I think Len, Sophie, and then also myself, and many different work has been done in the this crystalline symmetry considered systems. So in that case, your Hamiltonian is not only the simple Z2 type transition, but you have to take into account different crystalline symmetry. In that case, you somehow have to redefine your topological invariant, and it was many, actually nowadays many different materials show that instead of having a surface state, a 3D material can have a higher order topological state in 1D. Okay, if we zoom in to this it's again a spin momentum lock state, and it gives you quite nice topological 1D images. Okay, so this is part of the work we have done, but today I'm gonna talk about a little bit old-fashioned ideas. So instead of growing this very difficult 2D materials, I think for the moment only 1 or 2 groups in the world can do that. Is another idea about how to reduce dimensions of your material is simply to make it thinner and thinner. So if you imagine 3D TI, very simple case, and you put the thickness as thin as possible. Okay, so when the two surfaces getting very close to each other, what will happen here? I think there are a bunch of theoretical work has been done and show that because of your topological surface state has this very interesting wave function, which is the decay factor is a complex number, so that means they can alternate between the positive and negative. And when they coupled, of course, also this coupling can be quite naturally written in such oscillating, not only the amplitude but also the sign, basically driving the system into a positive gap or negative gap in the surface states. So actually, when this happens, we are basically facing again the topological, non-topological transitions within this 2D surface state. That means, well, once you have the gap in the surface, and then you are in this topological regime, you form a 1D edges. So that's why we go for this ultra thin system to see what's going to happen. And this is a very original work on the real number for the side of the gap or the thickness dependence. Yeah, because of course it's depend on the materials, parameters, and the actual thing. Because the material is layered, so they cannot go infinite small steps. It's always go one by one quantum layers, layers, sorry. And then the these numbers are not continuous but discrete numbers. So at the end, in the fields, people finally came to some common agreement theory, like for B2Se3, for example, the topological thickness is 3, 4, 5 with a reasonable side of the gap, and this is the regime we want to. Okay, so previously there are already some nice work, I would say quite impressive model work has been done by the team of Deschamps, and here they simply exfoliate the dye material. I think it was BSPS, quite complicated compounds, and then they managed to reach a certain regime which has a number of getting very close to Dirac points the resistance number reached to the H/2E square and quantum resistance number. And in this case, of course, when they apply the double gate, the electric field can also drive the system in and out of this topological state according to their measurement. But of course, you can see here it's quite complicated setup. And the most difficult part here is to kind of reproduce already the flakes. Because every time you do it, it's slightly different, and also too hard to make it. Yeah, sometimes they're not showing exactly the same results. So that gives us some space to explore with a different approach. One of the possibility, of course, is to grow it. Okay, you have MBE, which is grown method layer by layer, and here we use this BST, ternary compounds, and to again reproduce this topological transition with the thickness. And I think we made good progress here, but however, we have not seen any this topological state in inside the big bulk gap. And here there are pros and cons, of course, related to the simple approach. Okay, so this is one approach or try, and another one, which is the most relevant for our this talk, is we have a collaborator from Utrecht University, and they managed to grow the bismuth selenides nanoplates with a chemical method. So please don't ask me to describe that. I really don't know how that happened. But after they actually grow these beautiful nanoplates, they measure the STM. And then this gives a 4, 5, 6 quantum layer thickness. When they measure this, they actually see the edge state appears, and not below or above this value. So they give us this material in the solutions like this. And then, these are the meters. And then we simply just drop past one very diluted drop onto the substrates. And then we will find out very little pieces of these nanoplates, and then we make devices out of that. So here, this is how it looks on the FM. You can see this is just our markers on the substrates, and these are the plates. And the size is typically 600 nanometer. So that's the largest dimension I have in the material. So that's pretty small. But still, Feige, our student, is very talented to make these difficult devices, and he managed to contact this flake with 2 niobium leads, and manage at the end induce the superconductivity into the system. Okay, so now it comes to, of course, a little bit the physics that we want to probe. What would you see, or how to detect if you have the topological state? I mentioned that actually they are very flat. Okay, but anyway, these are actually uniform height of the nanoplate. There's basically no changes in the thickness. So here, if you want to probe these states, especially maybe there are still some bulk carriers because of the doping or unavoidable defects. The easiest way for us to see is by look at the profile of the current distribution when you have Josephson effects, and to measure that is to actually detect the field dependence of your critical current. So if you apply the out of plane field, you should see some Fraunhofer pattern like oscillation pattern. You have a homogeneous current distribution across the entire flake, and they will become a more straight-line behavior if you have only more strong contribution from the edges. Okay, so that's already quite a lot well-established methods, and many groups also have been reporting that. The only thing I want to maybe I want to go a bit faster here. For the ultrathin effects, the difference between the normal under bond states or the Marana-related bond state is relied on these the parity protections, therefore result in different periodicity in your supercurrent. So normally you will have a 2 pi periodicity of your supercurrent, but once you have this topological states protected by the parity, they tend to have a larger periods that becomes a 4 pi and also related to this effective half fermion charge. So there's a way to detect this effect. I will come to this later, but first let's take a look at this field dependence movement. So at the end, we managed to reduce supercurrents in such tiny flakes, and in this case, it's 6 nanometer thick. So it's actually a little bit higher than the theory part. But remember that we have done this in ambient environment, not capsulated. So our argument is that naturally they will be oxidized at the surfaces, so the effective thickness will be always lower, at least 1 nanometer lower. So then they can be quite well in this thicket regime. And then this is what we measure at the ICP data. And if you do this Fourier kind of transfer, and it will give you already good indication to have a higher density at the edge and much lower in the bulk. And in another device, which looks a bit funny in the profile, but we believe at the end we'll just measure one of the two flakes, because another one is much thinner. We see this. So this one is much stronger Fraunhofer pattern behavior, and you can tune it with the gates. Whatever. And then if you do the Fourier transfer, it gives you very tiny, very sharp density of currents at edges. And a little bit crazy part, if you increase the field, the outlet field, to like about 1 Tesla, they still exist. They modulated in all kinds of fashions, but no matter in which gate, you can always have this signature at pretty high fields. And this is quite impressive in some sense. And if we simply look at the largest field scale, this will give you the smallest dimension in your channel. That means the rest of the edge channel is about 10 nanometer. And this actually matches pretty well with the prediction in this theory. The extension or the decaying of your edge states is about to this 8 nanometer range. So this seems to match quite okay. And I think one of the funniest things we measured is this temperature dependence. So with such a little critical current, you can see it's about 4 nanoamp. The system pretty robustly to, here it comes a little right, but still up to 1.5 Kelvin. We can still measure this quite clearly, this supercurrent. And if you go a little bit to the detail, there's no saturation at lowest temperature. So this here is, if I'm not mistaken, I think the lowest temperature is 50 millikelvin. So there's no saturating behavior here. And it sounds a bit crazy, but if we think about this temperature dependence, the diffusive or ballistic or transparent or non-transparent, all this into account, the only way to produce this non-saturating behavior is to have a ballistic, long ballistic junction. That's quite typical behavior. And actually, if you compare to some simple simulations, just look at the shape, what they need to be, at least in this long junction regime, to match to any of this non-saturating behavior. And if we put the number of on its parameters, like the delta, the length, junction length, that means we have to have a extremely small Fermi velocity in this edge states. So this is something we're still trying to understand, and maybe I will see if at the end people ask that question. So now we are. Is there some signature? Okay, they're clearly edge state. They're match the prediction with the thickness. Are they really topological, these quantum spin-Hall states? Well, unfortunately, we cannot really measure this helicity by doing this simple Hall measurement, because there's still some bulk remaining. So this value will never be like perfect quantized. But then there are some observations which is not fully understood with this scenario. For example, if we go a little bit further in gates or depletion, it seems we can gap out our jump. So this is very hard to understand actually. If you have topological state, how can you gap it out? And then of course some more discussion should be considered is this electric field. They can also, when you apply the gates, you also apply quite large electric field, and these could also give extra effects, drive your system in and out from the topological state. So these may become multiple effects together. But then another side is this Shapiro step measurement. So previously I mentioned, if you have the topological state, your supercurrent changes from 2 pi to 4 pi period. And this can be seen when you measure the radiation response. So normally if you have a 2 pi state, you measure this quantized Shapiro step with HF over 2e. And then when you have 4 pi, you double the step. And this has not been seen in any of our devices. You could argue, okay, my ICRN is so small, we'll never be able to measure this about 1 gigahertz region. If you have to go to 100 megahertz or something like that, this is not really a reasonable region to measure. But still, I think together, this does not give a strong indication. There has to be topological. So is there any other possibilities? So, okay, this I already explained. 2 minutes. Okay. 3. Okay. I think I'm probably in time. Another possibility is completely wrong order, but that's okay. Yes. Previously, we studied another system with also business based, and we did some tight banding calculations. We found out that besides this beautiful, interesting hinge states, they can always host some robust 1D rush-bar states. This is actually this is something very well known in especially in STM measurement. I think people very commonly see this edge state just due to the they call it this potential difference, and you have very strong rush-bar terms come out. And of course, in that case, the difference is that the helical state cannot backscatter, but your rush-bar state, they have the backscatter is allowed. Even they are very robustly appearing at the edge. Once you do transports, the backscatter is allowed. So previously we measured also some edge states, but very broadened size. So this is somehow contradictory to what we have seen. We have very sharp and tiny edges as well. So all this together, they give us still a very like open questions. Are these states related to the topological phase, or it's just the trivial Rajba sleep but super localized? Okay, I think I will skip the second part. Let's stop here. I will simply go to the flash something through, but some of my collaborators that's work mainly done by Faiga, the Ben, as student understand in the simulations, and Alexander is a chair, and our collaborators in class. Thank you.
Okay, we have time for questions. Also on the slides that passed by at the end.
Yeah, actually.
Yeah.
I saw that you have some quantum dot data. So can you?
Okay, that's my
Yeah, that's good.
Yes. So which one to show? Maybe this one. Yeah. So the crazy part of this material is that once we go a little more to the Depletes region, there are no supercurrent anymore, but we start to see this localized quantum dot behavior, and very interestingly, we see this I-shaped behavior. Okay, could be related to this duplex, singlet states. However, you also see this loads of these stripes appearance, and also even go into this. Okay, this maybe the superconducting gap very weak. Maybe go into the gap. But this is very confusing part. We came with a very idealized idea. So I think previously from Nadin's group, they also see similar shape in graphene, and they interpret it as the ballistic transports. You have this bibarrel resonances here, and then in theory with some quantum dots near the contact. So then, of course, you can probe both resonance. So we also have this in mind and try to understand. Maybe that's. I think I can explain many of these features, and maybe we have more than one dot in our case.
Could it be localized in the bulk, Chuan?
Sorry?
Could it be localized within the bulk of your?
Yes, can be. And I mean, already, if it cannot be the surface states because topologically you can hardly to have a top.
Do you have an estimate to the charging energy of the dot?
Yes, we did a lot of estimation that always gives some pretty crazy number.
Crazy low, crazy high.
It's not enough to actually explain. And another thing, we don't really know the size of the dot, actually. The cool blockade. You see, it's just many things in theory. It's a bit hard to define where exactly they are. So we tried, all these stripes. We tried different scales. Some of them can fit, and if we use very bulk numbers for business sunlight, it turns to be the entire flame. Okay, that's a little bit hard to understand together with all these resonances. So, but these numbers is not known really. So we just put in maybe the number is wrong. In this, or simply understand the combination of these stripes and this dot-like behavior, that picture seems to be this one seems to be the most understandable.
Other questions?
When you have, I would like to come back to this discussion between states and alpha. That the big difference in way if you have what you show is that I want to be sure this is on the same system, but because of the oscillations you see persist to very high magnitude. It's true or not?
Yes.
Yeah. So and you have this is a way, in fact, you even find this confinement width, which is the nano. So to what extent this is compatible with the Rajba physics? Because if you have for the Rajba, then you have transverse delocalization, and so you should not see, you should lose, in fact, your oscillations at quite low field.
This one.
Yes.
You mean if you
Is
have
this compatible with your hashband picture? The fact that you keep, in fact, the supercurrent up to it's even up to 1 Tesla.
Yeah.
Is this compatible with your hashband picture?
Okay, when I'm saying this, probably in my mind it is, but because I mean, if it's a rush bar and both spins are simply spins. They are allowed on one channels, and they can carry the current. And once they start to interfere, why this is not?
Yeah, but because you have, but what about transverse delocalization of your system? You know what I did? Okay,
Yeah, I think I'm not getting.
Yeah, but when you have, for me, if you have, okay, we can discuss it after, but for me, this is not compatible with the fact that you cannot have transverse delocalization of your wave functions.
On the brush band.
Yeah, when you have a hash.
Okay, then I'd like to hear that.
No, because they are not edge states.
Okay. Well, we should discuss that.
Yes. Thank you for a great talk. A simple question. So the field was applied perpendicular. Okay. And then on your slide 16, where you have this temperature dependence of the physical current, there was a parameter D. And what is this? It was just delta? Yeah, the CO.
Yes. It's the yes.
Delta.
Transparency. Yes.
Transparency, not the gap transparency. Okay. Okay. Good. And you assume
it's
one
within
channel?
this Ellenberger equation formula. So,
Yeah. So with one
Yeah,
unique.
for the ballistic can be long because the only thing we have is the current length and transparency.
Yeah. So one global transparency for okay. No, you don't assume a distribution.
Yeah. We don't. Yeah. No. Yeah. It's one channel for that. Actually, we have another paper talking about different transparency, but
Okay. Okay.
Okay, so I propose maybe repeat